That's what I just said. All right, week 1 is done. 7 more to go.
How many people have we lost?
I don't know. And the only easy day was?
I don't know. Last Monday.
Yesterday. All right, so this week we are going to, really, the first day or two is going to be review from 309. So, why you say uh-oh?
I don't remember a thing from 309.
All right, well then I'll cover it again. So, I'm sure there's a lot of people that haven't had 309 in a long time. So, we're going to talk about Ohm's law. But before we can talk about Ohm's law and electricity, we got to talk about what makes electricity. So, we can talk about the atom. What's that? The atom. What can we just say about the atom? Well, it's the fundamental building block of nature. Fundamental building block of nature. It's the smallest particle of all matter. Just for comparison's sake, human hair is about, because it depends on the color, 1 million atoms wide. Well, what about the atom? They are composed of 3 subatomic particles. And if we were going to draw, we being me, well, let's think here. Let's use colors. There we go. Draw an atom. Let's see here. Make 4 little particles. So inside the middle is the nucleus. So the center is the nucleus. And I'll go back to black. And it contains protons. I'll make that red. Protons. And does anybody remember what charge protons have? Positive. Yeah, protons have a positive charge. Plus, or a positive. When we say it has a plus or positive charge, how do we know that?
Science.
Because science. Because reasons. It was arbitrary. It was just an arbitrary assignment. Hey, we're going to call that plus. All right, there you go. That's plus. So that has a charge, and we call that a plus. And the protons are in here, and made them red, and have a little plus charge. And also inside of the nucleus, we have neutrons. And they shall be blue. And neutrons have what kind of charge?
Neutral.
Have a neutral charge. And then orbiting around, we're going to have what? Electrons. So inside the nucleus we have those. Outside and orbiting we have electrons. Electrons orbit the nucleus We'll say in shells. S-H-E, shells. All right, and they have a negative. So we'll give them a little negative. So all right, so we got electrons with a negative charge. We have protons with a positive charge and neutrons with a neutral charge. And as I had mentioned in 309, what I've drawn here is a very basic two-dimensional model of the atom. And of course, the atom is not two-dimensional, it's three-dimensional. But it's, number one, I'm not good at drawing three-dimensional. Number two, this is kind of the way the book shows it. And so we're just going to go with that. But some renditions of the atom show that the atoms kind of go around in sort of a 3D pattern. But that's even not exactly accurate, because when it comes down to it, these little atoms actually don't orbit like planets. I find out that they really more like buzz. They have a bunch of energy and they buzz around. But the two-dimension and three-dimension kind of works better for the concept of how it works. So when we look at an atom, the interesting thing about an atom, unless it's an ion, but a basic atom, is you have equal amounts of everything, the basic atom. So if I have 2 protons, I must also have 2 neutrons, and I must also have 2 electrons. And unless I'm missing one or the other, we'll get into that in a second. So I'll write that here. If, or say an atom with an extra electron. So if I have an extra electron, what kind of charge, extra charge do I have? This all balances out. 2 pluses and 2 minuses, I'm balanced. But if I add a negative, what do I get? Do I have more negative or more positive?
Negative.
All right, so if I have add an extra electron, an atom with an extra electron is a negative ion. So an atom with an extra proton is what?
Positive.
Yeah, positive. So if I gain an electron or lose a proton, it's a negative ion. Or if I lose an electron, or say I said lose an electron or gain a proton, it is a positive ion. There we go. All right. Now when I've said that, what? Did I move too much for you?
Wait.
All right, because it was right there. I mean, you still see it. It really didn't change a whole lot. Just
Yeah, you didn't change anything.
okay. All right. So I have a whole lot of stuff I had to. I went way too deep one year. Too much. I get into Bohr versus Schrodinger theories and stuff. We don't need to do that. All right. So when we look at an atom, and I said there's this, they orbit around, and we call them a what? Shells. Okay, so they orbit around in shells. Now the thing about an atom, and the thing that we're going to kind of look at, and the difference between an insulator and a conductor, has to do with how these electrons orbit around in their little shells. And the amount and where the electrons are placed has to do whether or not it easily gives off these electrons, which is the flow of electricity, or it doesn't. So when the electrons, I like to think about this, when the electrons they're going around in an orbit. So we could say, well, and I'm just kind of, this isn't entirely accurate, we can go with it. They have, we can say centrifugal force, and they want to like spin out and leave. But what's holding them in place? What keeps them from wanting to just wander off and go away? The magnetic field, right? And we'll talk about this in a little bit. I'll talk about it now, right? So it has a magnetic field. So when we consider a magnetic field, or another way of saying it is they each have a charge. So like charges. Like charges do what?
Attract.
They attract. Do I get into that? Yeah, that sounds better. They repel. Huh? always look at my notes. When do I get into this? Okay, so like charges repel. They don't like each other. They want to go. Well, it's interesting they say that. Then you can wonder, well, why come they're not repelling? But heck if I know. All right, like charges repel, and what do I want to say here? Unlike, dissimilar, opposite. So charges attract. All right, so we have a little model up here. And so the electrons are spinning around. They have some force that wants to throw them away from the center of the atom. But yet there's this attraction between the positive and the negative that wants to pull them back in. So everything's in balance and they're fine. But the more I get out away from here, I'll put in another shell. That is not working well. Okay. Another shell, sorry. Another shell. And hang on. Do the magic of. It's not easy up here, man. All right. So we'll make another shell out here. This is going much better. And as these electrons start to get in another shell further and further away, they're going to, we could say they have a little more energy out here spinning, and they have a little bit less attraction. So these electrons, as they get out and further in the shells, they tend to spin off a little bit easier, free electrons. So we can actually harvest them and thus get the flow of electricity. So when we look at that, we can next kind of talk about how these shells work. So how many electrons can go in a shell? So the number of electrons in a shell is 2n squared, where n is the number of the shell. So in the first shell, so we go like this, 2n squared, or the first shell, 1 squared. How many electrons can go in that one? Well, what is 1 squared? 1 times 1 is 2. One times, I'm getting there. 1 squared is 1 times 1, which is 1 times 2 is 2. So you can have 2 electrons in the first shell. All right, how many can we put in the second shell? 2 times 2 squared equals, well, 2 squared is
4.
Don't yell at wrong numbers. It's hard. 2 squared is, come on, you guys got to play along. 4 times 2 is 8. So we have 8 electrons in the second shell. How about the third shell? 18, because 3 squared is 9 times 2 is 18. And we'll go fourth shell. 2 times the fourth shell is 4 squared is 16 times 2 is 32 electrons. In the third, in the fourth. All right, so that's the basic formula of what? What is that the formula? What am I talking about? Electrons what? What about electrons?
Shells.
Electrons, shells. What's that?
Electrons per shell.
Electrons per shell. So if I'm building electrons, do you always you don't always have to fill up a shell before you move on to the next one. That's kind of the interesting thing about it, because you sort of think that maybe that's the way it works, but it isn't the way it works. It isn't the way it works. So if we take a look at some different different types. I had some good ones here. Oh, here we go. So we look at gold. So let's see, gold. Gold. If I look at gold, gold has 29 electrons. How many protons does it have? 29. How many neutrons does it have? All right, but I'm more interested in the electrons. So it has electrons. Well, how many can go in the first shell?
2.
2. All right, so it happens to have 2 in the first shell. How many can go in the second?
8.
8. Well, it does have 8 in the second. How many in third? 18. And how many in the last one?
1.
It can have 32, but it only has 1. So you got this lonely electron way out there in the fourth shell. So do you think gold is actually going to be able to give off that electron easy?
Yes.
Absolutely. Let's see, silver. Silver has 47 electrons. And rather than you guessing, it'd be 2, 8. So far, so good? 18, so far, so good? Huh?
Looking great.
What?
Looking great.
All right. 18. What comes next?
32.
32. But you know what? It's going to go 18 again. And then 1.
Makes sense.
Oops, this was copper, not gold. I knew something was wrong. That's copper.
I told you it wasn't looking right.
I know. Here's gold. Here's gold. I'm kind of jumping around. Gold has a lot of electrons, 79. What are you lost about?
Well, you're scribbling stuff out.
I just one thing. One thing.
You messed up one thing, I got lost.
Okay, it's not really gold. It was copper that had 29 electrons. Sorry. Same thing. Gold. Gold has 79.
Wait, does it always have to have 2 electrons in the first shell?
Okay, so my point was it doesn't necessarily have to fill them up as it goes. And so you can see how it doesn't. So 18 right here, it should have been 32 if it fills it up. So it doesn't. It doesn't necessarily have to fill them up, the shells. It doesn't have to. But what's the most you can have in the first one? 2. What's the most you can have in the second?
8.
Okay, and in this case, it does fill it up. It's just an example. It's not like I'm going to have you guys okay in the back row? You want me to wait till you're done?
No, I was explaining about the shell section. I didn't.
How does that work for you guys when I'm talking and then he's talking and then I get done? Now he's like, well, okay, now that you explained that, what did he say while you were explaining that? It's got to be confusing for you.
I didn't understand.
What's that?
I didn't understand.
I know, because you guys are having your own conversation back there. So you were talking about something else while I was talking about this. So you got lost. All right, want me to slow down and go back again? Okay, you with me? Okay. Try it again. So in an electron, you're with me, right?
Yep.
Because you look like I already lost you.
Yeah, I'm trying to write down notes.
All right, in an electron, in an atom, the electron orbits around in a what? What's it called?
Shell.
A shell. All right. So we have, this is the nucleus. What's inside the nucleus? All right, protons and neutrons. And then orbiting around in the shell, we have electrons. How many and this is a shell. How many electrons can I have in the first shell?
2.
2. Because of the formula, 2n squared. N is what?
Number of shells.
The number of the shell. All right, so in the first shell, I can have 2. What about the second shell? How many can I have as a maximum? 8. All right, so some of you paint because it's 2 times 2 squared. 2 squared is 4 times 2 is 8. So I can have 8 of them. 1, 2, 3, 4, 5, 6, 7, 8. Does it have to have 2 and does it have to have 8? No, it's just the maximum. So for example, gold has 79 electrons. Think they all fit in the first shell?
I'm going to go with no.
You're going to go with no. How come?
Only 2 fit the first.
Because you can only have a maximum of 2. Do you have to have 2?
No, you can have 1.
No. Good thing. But there still happens to be 2. Just happens to be 2 in that gold. All right. How many is in the second shell? This is the second shell I'm writing right here. How many?
8.
8. And guess what? It does have 8. What's the maximum in the next shell?
18.
And it does have 18. Wow, it's just looking out great. How many can have it in the Third. 32. And it does. How many can it have in the next shell?
18.
I think my calculator.
No, it's gonna be
Right there.
5.
32. 1, 2, 3, 4, 5. Yeah, go ahead.
25.
2 times 5 squared.
50.
How many?
50.
50. Can have 50. Well, there's 79, so let me see. Where are we at here? 32 plus 18 plus 8 plus 2. We're at 60, so we have how many more left? 19, and I can have 50, and I can have 50 here. So how many do you think are there?
18 and 1.
There's an 18 and 1.
There's 18. Why 18? I don't know. I'm not God. I didn't make it. That's why he made it. There's 18 there, and there's 1 out there. So this 1 out here, because it's way out there, and have 1 way out here and 1 way out here. I'm just looking at a pattern here. I have copper, silver, and gold. What do copper, silver, and gold all have in common that you know about? They're excellent conductors. Just noticing a pattern here. What is it about all of them that make them excellent conductors?
One electron in the outer shell.
Got 1 way out there. What's that?
He said they all ended 1.
They all end in 1. Yep, they all have 1. Yes.
I was just wondering, since you said it's just the way it is, there's not really a whole lot of rhyme or reason to the amount in the shells past that point. Are you gonna ask us to like fill shells out using the atomic number?
Have I showed you how to read an atomic chart?
Yeah, but it's just like with silver, you have that last one hanging out by there because of the conductor. But I was just wondering if you were gonna, give us a whole bunch of just random atoms and have us fill the shells out. Hey.
Well, if I were going to do that, I'd have to teach you how to read the periodic table of elements, how to do that, right? Haven't got there yet, have I? So no. Did you want me to teach you that?
No,
You sure? I got it in my notes. I mean, here we go. I got the periodic table right there. We can do it. I am prepared.
Are you? I'll call your bluff.
It really is in the notes. And everything.
Teach him on Saturday.
Yeah. That page is out of whack. All right. Yes.
So you could have an infinite number of shells.
I don't know. There's a limit. You just have to read the table of the elements, and there's an actual limit to what it is. It's all on here. Whatever this is, there you go. And I don't have that memorized, and I don't know what the most is or the least or anything like that. It's aircraft mechanic, man. All right, but there are some questions in the FA, and you kind of have to know this. What's that?
Don't sell yourself short.
I know what I know. All right. So, all right, you with me back there? It looks like I lost you again. You're having your own conversation again. You want to come up here where it's easier to pay attention? You sure? Okay. Well, we'll give it a shot for a few more minutes back there. But if it doesn't work out, I'll have you come up here and we'll see if that works better.
You can sit next to Tim.
No, this is my spot.
No, I think right there's a good spot.
Because that is blocking the screen. And then
We'll figure something out, won't we? All right. So we have a special name for this outermost valence, whatever it might be, the outermost valence ring, the last one out there. So the outermost.
Good word.
Outermost, you like that word? All right. Outermost shell electrons are called the valence electrons. And because I think it comes up later on, how fast do electrons move?
Pretty fast. Get out.
How fast is the speed of light?
186 miles per second.
It's at least 100. All right. I went all over the place here.
Hey Siri. I was really hoping like 5 phones would take it.
All right, we'll pick it up here. Okay, so that leads me to a definition of something we can call free electron. You like the sound of, wow, if I can only spell it. T-L-E-L-E-C-T-R. Okay, got it. Free electron. Well, that's really, have you heard of this one?
Probably not.
BOGO? So you buy one electron, you get one free. Yeah, that's not really what it is. Not like that. All right, free electron. And say an electron. An electron in the valence ring that is not tightly bound to the nucleus. An electron in the valence ring. What's the valence ring?
Shell.
It's ring, valence shell, same words. That is not tightly bound to the nucleus. And therefore, free, here's our word, free to jump to another atom. An atom moving from an atom. That's not what I wanted to write. I wanted to write electron. An electron moving from one atom to another is what? Thank you for answering. Electrical current. So that is current. It's just those electrons moving along in one way. We can say an atom's ability ability or lack of ability to gain or lose an electron defines its classification. What do I mean by classification?
I would guess you're gonna tell me.
There, no, he's paying attention over here. All right, so what type of classifications? So we can say we have three types, three properties or three classifications. Three properties or classification, since I use that word. Three classifications. And those three classifications are, 1, conductor. So an atom makeup of an, whatever it is it's made up of, these atoms can make up a conductor. It could be a insulator. Or it can be well, it's not a conductor, it's not an insulator, it's kind of
Semiconductor.
Semiconductor.
Look at this guy here.
Semiconductor. Let's talk about the conductor first. What makes something a conductor? Why does one thing conduct electricity and allow electrons to flow and another doesn't? So conductor. Well, a conductor has less than 1/2 the allowable less than 1/2 of the allowable valence electrons. So if we take a look, I'm going to scroll back up at gold. Gold, what we're in the 6 shell. He had 6 shells, yes?
Yeah. Yes.
Go up here. 1, 2, 3, 4, 5, 6. So the valence electron, that's the valence ring, is the 6th one. And it can have how many electrons?
Less than
50?
No.
36 times 2.
So it'll be
72.
72. So gold can have 72 electrons, but it only has 1. Is that less than half?
Yeah.
Okay, so does that make it a conductor? Yeah, pretty nice one, I would say. All right. Why? Because the outermost ones are loosely held. They're the free electrons, and they're able to kind of split off on their own and move more easy. An insulator. Well, what do you suppose an insulator is? Insulator has more than 1/2 of the allowable valence electrons. And I don't have a specific atomic example, but what are some good examples of an insulator? Rubber, wood,
Plastic.
glass, plastic,
Metal?
air. Air's a good one.
Carbon.
I don't think so. No. I heard water. What do you think of water?
Pure water.
Semiconductor.
Pure water. Pure water is. But I'm not going to write that because that would just be. What are some examples of a good conductor?
Copper. Gold.
silver.
Copper. I heard gold. Or did you say coal?
I
Gold.
didn't say it.
There's the pen steel in front.
What else?
Silver.
Silver. Aluminum.
Dude, I love this
Steel.
Steel. All right. So what are wires made out of in homes and cars and planes and boats? A lot of copper. Mostly copper. Why? Cheaper. There you go. I've heard it said that silver is actually the best, but there's a problem with silver. Corrodes, oxidizes very fast. Therefore, gold becomes the go-to for this, something that is the best one that doesn't have that oxidation problem. So you find gold conductors in very expensive electronics.
Cell phones.
Well, they cell phones. In cars, they'll use them on the airbag components. How about aluminum?
Yeah.
Well, there was a period of time, I think around the 70s, mid-70s, where aluminum became the go-to. What would aluminum have over copper, gold, or copper at least?
Malleable.
There you go. It's lighter and what?
Malleable.
Malleable. Probably cheaper. I'm just guessing on that one. It's cheaper, lighter. But aluminum has some corrosion problems on its own. And so there were some aircraft that were made with aluminum wires. The ADs came out. You had to replace the aluminum wires. Homes have them, some homes, and then they also have their own ADs on them. Not really, but they have significant problems, and you have to have special greases and connections to put them together and stuff. But inside of an aircraft, the return path is the ground, and that means that everything is going through the airframe, which is generally aluminum. All right. What about fiberglass? Where would that come in on this? All right, so if we have a fiberglass aircraft, not such a good conductor. All right, then we have semiconductor. Well, it's kind of an in-between. So in between conductor and insulator. We'll talk more about these when we get into in a few more weeks. There's germanium. It's one of Michael Jackson's brothers. And what's his name? Yeah. It's named after him. And silicon each have 4 valence electrons. So if they have 4 valence electrons, which ring do you think they're in? Second one, and how many can you have in the second? Up to 8. So it's kind of messes with the formula. All right, but there we go with that. So, all right, and how fast do these electrons move around?
Speed of light.
From both.
Speed of light. All right.
No, just me.
Speed of light is how much?
It's fast.
186,000 miles per second. And never abbreviate that MPS. Could be like, what's that, meters per second or miles per second? I forget. All right, move over a little bit. Hey, I already covered this. Electricity is a movement of electrons from one to another. They move about the speed of light. Fundamental principle is attraction and repulsion. Unlike charges do what? Attract. So protons are going to attract electrons and create stability, and like charges repel. So if that's all true, and I have a wire, and through the magic of my right pad, I enlarged this wire, and we were to look into there, and we were to see all of these little atoms made out of copper, and we'll just put the little valence ring in there with some of the, it's a little orbit. These are our little electrons flowing around in there. And so what's happening inside of here when we do this? Of course, they all share.
Electrons are jumping from atom to atom.
They are. So maybe I shouldn't have made so much. It's taking too long there. So gotta think this through. Think it through, man. All right, so we'll just make it a little smaller here. All right, so really, here's a piece of wire, and it's just sitting there. We've looked in there. These electrons, they kind of move around a little bit. They're not really stable. They come to the right, to the left. Some are going right, some are left, some up, down. All right, but if I take this and I hook it up to a battery, so I'm going to bring this around. I'm going to say, ooh, I got to hook it up to a battery. So here's my battery. So battery, that's the positive, that's the negative, that's the positive, that's the negative. This is the symbol for a multi-cell battery. Now the old school convention was every time you did this is a single cell battery, but every time you did this, that's 2 volts. So that's a 4 volt, 6, 8, 10, 12. So 12. So every time you wanted to write a schematic with a 12 volt battery, you did this. And guess what? If you never drew a schematic with a 24 volt because you were there all day doing those little lines. But thankfully the convention changed, and it's okay. That's just multi-cell. It can be as many volts as you want. Just write the voltage next to it. So here we have a multi-cell. I'm going to come up here, and I'm going to go, there's my positive, and bring this down here to the negative side. So the long side is the positive, and the short is the negative. All right, so now I've hooked it up to there. Well, what's going on inside of this battery? There's a bunch of plates in there, just like this. And these plates have a chemical reaction going on, and we'll talk about this in a few more weeks, where there is going to be an extra amount of electrons all built up on these negative plates. And these negative plates actually touch. And these positive plates touch. And all these negative ones. Well, guess what's built up along the positive side? Well, a whole bunch of atoms that are deficient in electrons, right? So we have a bunch of, we can say positive ions there. They're missing electrons. So what do they want up here in the positive plate? They want electrons. They're missing them. The chemical reaction in the battery stripped them out, stuck them over here on the positive plate. And these, the negative plates. The negative plate's got a whole bunch of extra electrons. All right, so what happens when I connect this, well, we could do this and say, well, wait a minute, let's don't connect it yet. I got a switch. So here's a switch, right? All right, switch. What does around mean? Terminal. What if it was like this? Momentary. As soon as I let go, it opens up. All right. So I've got this, and let's see, we're going to close it. So electrons are going to flow. Well, which way are they going to flow?
Positive to negative.
All right, so they are actually going to flow this way. From negative to positive. Because like charges repel, and unlike attract. So what is the plus going to attract?
Negative.
Yep. Well, I was going to personify it. It says, need more electrons. Need more electrons. There, that's what that's saying. Need more electrons. All right. So it's attracting them, and this one is, we got too many. Right? So it's bumping off electrons. The electrons are going to go this way. They're going to come into here. They're going to bump these electrons, and they're going to start moving all this way and over to here and start collecting back over here and start filling up what was missing. And when it does that and fills them all up, then the battery needs to be recharged, which is to strip them back the other way. So the flow of electricity is from what?
Negative to
positive. Negative to positive. And that is called the electron theory flow. Electron flow theory. I think that sounds better. Electron. Now, what was the old way of thinking? Positive and negative. So positive to negative. It is positive. Is called what? Conventional? Conventional theory. So what's nice about anybody know what's so nice about the positive and negative, the conventional theory?
Makes more sense.
They make more sense. Schematics are written that way. Schematics are actually written in a way that it's much easier to follow something positive to negative. And the reason why I say that, and I'll just throw this out real quick, you don't have to copy this, but if you have it, and I'll make a very simple schematic. All right, so I have a battery. If you're looking at a schematic for an aircraft, it's going to show a battery with this little symbol here. There, let's draw it nice.
Looks like a ground cap.
It is a ground. So it's a ground. It comes right off the battery. And then I'm going to have a load. So I can have a motor. I can have a light with a switch. This is a very simple one, right? And some other sort of load over here. But of course, they're not this nicely laid out. They go all over the place, and you have all kinds of different stuff. And I want to, and these are right in front of you, but it can be kind of hidden, these little ground symbols all over the place. And so if I want to figure out the flow, I go, okay, well, how's my motor working? So you start here, and you got to find where this wire terminates. Somewhere, it comes up into here, comes up into the ground, then through and back. That's very difficult. It's much easier to say, okay, if I want to see the flow, I can see the flow goes this way, down through the motor, then out of the ground and backwards. Now, doing it this way, which theory is this?
Conventional.
It's conventional. Going from the negative up,
Electron theory.
electrons. So it really doesn't matter. It's going to work both ways. In fact, to prove the point, the reason why it's this way, partially, is they didn't figure this out until like some time in the, I don't know, it was like 40s or 50s that it actually flowed the other way. To electron microscopes and stuff like that. It was just, when I went to school, it was positive and negative. That's how it is. So it doesn't matter. It'll work both ways if you're talking about this. And it starts to matter when you're talking about solid state stuff. But as far as this goes, it's fine. So, all right. There we go. And that sounds like a good place to take a break.